Can you start thinking, like, what is the input? Output, of course, we can put it as like a speed or whatever. What are the input? Start thinking. You guys want to be engineer, right? You can design a controller that ride a bicycle. Triggers. Which you do. You are a controller and you ride your bicycle. Your brain does this stuff. What does that mean? We can start. So we are talking about the model. Okay. So far we have covered two models. One, transfer function. The other one, state space. You know how to go back and forth, etc. First, you have ODE. When you attempt modeling, you have ODE. From ODE, you go to transfer function or a state space, and you go back and forth. The next modeling technique that is important for us is impulse response. Okay? So let's cover the impulse response today. We started this last time. Okay. We start with the delta function. Okay? Delta function, remember we discussed, it's not a function. You cannot say delta at 0 is infinity, is stuff like this. Don't say that. Always think about a pulse with some base. It's really small. The base is epsilon, height is 1 over epsilon. That's what we need to think. It's an approximation, it's a technique that undergraduate education in some school now have created so that they don't teach generalized function. Okay? That's what it is. And it works to some extent. Because in those programs that they don't cover this, literally they don't use impulse response. Literally, look at your 4 years, how many you have heard impulse response, you've heard convolution, etc. But essentially you work with transfer function. Okay? So that's one of the another. So that's what you should, this is an impulse sitting at time t1. That pulse. Okay. Delta is the base of it. The limit of this is delta function. Now, what is that limit? That's the key. Okay? The limit, the arrow in there. What kind of an object is this? What sort of thing is? You don't touch it. Okay? At this time, you learn it like this. And we went through this. Obviously, the antipole of this is 1 for any delta. As delta goes to 0 is 1. So the first thing, the antipole of delta is 1. Okay, we learn this. Alright. What we learn, which is very, very important, why delta function for the continuous suddenly is something. Why is that so? Okay? Remember what I told you yesterday? In fact, the last lecture is not this. I said any arbitrary signal that you pick up is what? Weighted sum of infinitely many delta function. And then if you know the superposition law, this is a very good thing to use as a model. Response to a delta. Okay? It's a weighted sum, so I can find response to any arbitrary signal as long as my device is linear superposition law as long as I know response to it. This is the idea, understood? And I went through this. You have a function. This is the key. This is
I just
first
muted our
class
mic, that's it.
on the lecture.
Okay.
Remember that I changed the F to U because I'm on it notation wise. Ended up with this. We ended up with this. I framed it out so that you understand. Any arbitrary signal, look at what I said. Any arbitrary signal equals. This means something. Values delta sitting at time top goes from minus infinity to plus infinity. Each of them with this weight. When it's sitting at tau, the weight is weighted sum of infinity many delta. Is that clear? So that's the key. So with this, now we can say, okay, let's work it out. We check the Dirac system. Only assumption is linearity, L. That is superposition law, okay? Let's create a notation for us. Output signal, input signal. Output equal this device S, whatever it is, we call it operator. Act on a U and gives you S. One. So S is we can think about it as an operator, notation wise. S acting on U gives you. So we have this. Okay? But my U is this. I can represent U as this weighted sum of zillions of delta functions. Is that clear? So y equal SU, instead of U, I can put this guy. That's what I do. So y of t at time t is this. S, the operator, linear operator that we have, acting on this signal, which is the U. Okay? What is the superposition law? Superposition law is, in fact, maybe you should really think about, response of the weighted sum of input is the weighted sum of the output, right? Think about this mathematically. This is English language sentences to begin with. Translate to mathematics. Okay? Very trivial. It just is a representation of that language in mathematical term. Response is S operator. If I put a sum of a bunch of signal, okay? When I say y equal S U. Suppose U is a sum of bunch of signal, weighted sum of bunch of signal, alpha I from W R. Linearity means what? Y will be weighted the same weight of the sum of responses, right? So what does that mean? That means sigma and S, they commute. You see, S can go inside. That's the definition of that English language that you said, okay? So we do the same thing. This is a sum. This is a sum. S can come inside. Make sense? You follow? Okay, so response would be S acting on the delta times the weight. Sum of the weighted response. Is that clear? Are we good? Let's call this thing HT comma tau. So delta sitting here, response to the delta. Another word, picture is this. Picture is this. This is your S operator. Here, time tau, the delta sitting here. The response is HT comma tau. That's what I'm using. Is that clear? Are we good? The first thing you got, so here, that's what I got. HT comma tau is called impulse response. If I know HT comma tau, which is response to the delta, YT would be this. This has a name. Write it down. It's called superposition integral. That has a name. Response piecewise response of a delta function time tau. It's complicated because H response is a function of t and tau, two variable. You change the delta in various time, response changes, okay? It's a function of tau. The place, is the place the delta sitting, okay, at the input. So that's the first thing that we got. It's called superpositionality. Okay? It's not useful, this guy. Nobody uses this. This is a beginning. Okay? Now we want to make it useful. Bring time invariant into the picture. Then suddenly becomes very useful. This was only under L linearity gave you this. Now think about it. I bring time invariant into the picture. What would happen if I bring time invariant into the picture? Suddenly things becomes useful. Okay? Remember one thing. If I want to use this, you want to see the complexity of it? If I want to use this, I need to know ht comma tau. Yes? As soon as you change the tau, ht comma tau changes. So I have to put zillions of delta in various tau and find ht. Is that clear? Suddenly you see this is profoundly complicated because ht, you put the delta, you have to find the response. At this, change it to this, another response is a function of tau. That's the complexity. Okay? Okay. Before getting to the time invariant, let's look at this. This goes from minus infinity to plus infinity. I think it's important to bring assumption. If the system is relaxed at t naught, okay, so suppose your system is relaxed at t naught, you can write minus infinity to plus infinity, minus infinity to t naught, and t naught to infinity. If you are relaxed, this just goes away. So as soon as you put the relaxed assumption, write it down. The lower limit is t naught. If you are relaxed at t naught, your lower limit is t naught. So if I choose L plus R means relaxed. Lower limit is t naught. Is that good? Okay. Let's look at the upper limit. Let's look at the upper limit. So this is for L plus R. As soon as I put a condition, an assumption, things changes. Okay? Relaxedness means lower limit is of minus infinity, put t naught, make it easier. Okay. I want to put the causality now. Okay? As soon as you put the causality, linear, relax, get respect to t naught. Okay? Causality, I claim, as soon as you put the causality, if the device is causal, upper limit is t. Same number that you want. If you want to find y at time 5, you go from t naught to 5. Is that clear? Why the causality does that? Look at this. If I put a delta function, if this device is causal, what sort of a structure imposed upon H as soon as you say causal? So think about it like, so I put the delta here at tau, right? This is tau. This is device, and I'm going to get ht comma tau. Device is causal. So what does that mean?
All factor for 0 is 0?
Absolutely. Up to this point, you have to be 0. Can I say in English language, you put in your head, you never forget? When somebody says causal means this, nothing in, nothing out. Understood? Write it down. Bring it to the point of common sense. Nothing in, nothing out. It doesn't see the future, okay? Whatever it is. Actually, really, this is what it, doing it, causality say nothing in, nothing out. End of the story. Non-causal is not true. Think about moving average filter. Non-causal is not true. Because response is a function of future output as well. So you cannot say nothing in. Make sense? Okay. So HT comma tau, as they pointed out, has to be zero. That follows this. For every less than. Okay. So as soon as lower limit and upper limit changes by the fact that you put relaxance and causality, okay? Now look, still is complicated. Still, we have to bring time invariant into it. So it has to be LTI, and then maybe relax and causal, etc. We can add it. Let's look at the time invariant. Okay. Remember the time invariant definition of it.
Yes.
Shift invariant, right? If you go to your lab, perform experiment today, measure this one. If you go tomorrow, do the same things, you see the same response, right? It's called shift invariant. Shift invariant. Okay? So let's make this guy mathematical, okay? Define a shift operator that changes the signal by whatever amount you want, by alpha. In other words, this is a shift operator acting in a signal U, create ut minus alpha. Shift the signal, okay? Call it shift operator. So when you say the system is LTI, okay, so I define this. Again, English language is shift up invariance. I'm going to convert it to the mathematic. Mathematic means things that you can work with. Okay? So you have device which is S operator, and you have a shifting value. All it means LTI, these two can promote to. Okay? So let's look at. Suppose I have the signal U, and this is response. Okay? Shift the output by alpha. Time invariant, it says shifting the output is same as shifting the input. Okay? That's what it says. Okay? So I'm using this. In other words, look at this. Shift operator and S, they commute, they flip. Now let's look at, let's see what this guy gives us. Okay? Let's pay attention to this as we go step by step, and stop me if you don't understand. I put a delta at time tau. Response is ht comma tau. You start with this. Okay? I'm going to shift it by alpha. Okay? I'm going to shift it by alpha. This response, I'm going to shift it by alpha. So I apply Q alpha to this. Therefore, Q alpha applies to this as well. Is that clear? Okay. What did we learn? This guy commute. Right? So I can write it S Q alpha delta minus. Correct? Okay. Go forward. So it would be what? As you shift the delta, the T by alpha, so it would be T minus tau minus alpha. Correct? That's what it. So what I got is the shifted of this. Shifted of this is ht minus alpha tau. This guy is this. T was shifted by alpha. Is equal. This means delta that's sitting at the time tau plus alpha. So I can write it. Response to this would be ht comma tau plus. Right? alpha. Okay? And any t. Just a little algebra. Replace t by t plus alpha in this case. I can do it. For any t, this is correct, in particular t plus alpha. So what I got ht comma tau equal ht plus alpha and tau plus alpha. Now I'm going to choose alpha to be equal minus tau. So what I got ht comma tau is equal ht minus tau. That's it. That's it. You know what does that mean? You lost one degree of freedom. H that was function of two variable, now is function of one variable, t minus tau. Suddenly becomes hugely useful. Hugely useful. Okay. So in an LTI case, you lose 1 degree of freedom in your impulse response. Okay? Let's see, from here you can see, like if I know, think about this, how significant it is when I do. If I want to find, say, response to a delta that's sitting at point tau, it is sufficient for me to know response if delta sitting at time 0. If I know the response sitting at time 0, delta to another tau equals 0, for any tau I can find it from that is shifting. I just need to know one rather than infinitely many. Understand this? How significant this step is? Suddenly impulse response becomes useful for engineers. If I want to find the response at tau, I can only find the response at 0. How to be 0? Let's call it h of t. Shifted by tau. Sort of shifting. So you need to know only one, which is response to a delta sitting at 0. Okay. This is it. This is it. As soon as you say LTI, 1 degree of freedom is gone. Function of 2 variables becomes function of 1 variable. Okay. Your superposition becomes something that for years you guys played with it, so-called convolution. Instead of ht comma tau, which was superposition analytical, you put ht minus tau. Now this has a name that you are very familiar with. It's called convolution. Okay? That's the way you get to this. If you are causal t, so I write linear, time invariant, causal, relax. Okay? That's what they taught you for so many years here. Okay? Make sense? Superposition one for the time value, not useful. This guy is useful. Okay? Do you, in a program like here, the ERWSU, have you used it in impulse response? You're familiar with it, you're not using it. Is it very useful for engineering? Yes, it is. Okay? Now, one thing about time invariant devices, shift invariant devices, when you start your system operating at a certain time t0, it's a global time. Okay? Starting at t0, you can always reset the code. That comes from read. Write it down. In LTI device, when I operate, I can reset the time. You cannot do this if it's time valid. I cannot reset your age. You're a system. T0 cannot be reset in a time value. Only in LTI you can reset. In other words, you can say T0 without loss of generality, make it 0. When you start working, no matter what's the global time, plug it 0, so T0 becomes 0. You fall. Not true in time value. Okay? The difficulty is you have to pay attention to this because we didn't used to make time-varying devices. Now when you start working, you realize life has changed. It's time-varying. The craziest stuff is happening through the adaptation, non-linear engineering, etc., etc. It is moving unbelievable. I cannot explain to you how fast stuff is changing. How fast it's changing. It's a shocking moment to be alive and to see it. Literally, it's a shocking moment. Okay? So, you have been in a location very narrow, seesaw, timing valley. You played with few devices, etc. And then suddenly things are changing. And it is important to be aware of this. Okay? So when you look at this, I'm looking at, put the delta only at time 0, call it h of t. And the notations, remember that undergraduate, they use it. Output is a convolution of impulse response. All you need to know is a response of a delta that's sitting at time 0. This is useful now. This is useful. Okay? Few little things that give us, we want to learn, like, connect the impulse response to a transfer function. What's the relationship with this? So I need to figure it out. What's the Laplace of, say, delta, for example? Okay? Let's look at, you guys know a step function, right? Is that clear? All of you know a step function. Say it again.
Step function. What?
A step function.
Yes.
Yeah?
Yes.
Okay. Step function is, there are certain signal, we call it the standard signal. Okay? It's a tool for engineers. One of them is a step, ramp, parabola. A step is a critical. What the step means, why they suddenly choose this step? A step is sudden changes. Sudden changes. You were here, suddenly you jump to this. Okay? Change. It turned out the reason that the step is so significant for us is that when I look at, for example, cruise control for a car, for example, say you are driving a car, okay? You say you were driving like a 45, you want to say, hey, go to 55, for example. Okay? System respond to you. Okay? We have to look at the way the system responds. Finally, it goes to the 55, but how does it go? Does it overshoot to 80 and then come back? Or does it undershoot like your 45? Actually, there's a generation of cars, they did this. Stupidly, they did this. I think it was a GM, I don't remember exactly year of it. So you are here, you want to go 55, it has an undershooting. It drops to 40 or something like a few months, and then shoots up. How do you like to drive such a car? Or shooting up, go overshoot to like a 65, and then come back to 55. Do you understand this? All of them has to be engineered. If you take an elevator, you say, I want to go to the second floor. Oh, no, third floor, I want to go to. How do I land you? I can drop you there. How do I do it? I can drop you there. Oh, it has to be engineered. How am I going to land you? Okay? So, a step function, for example, for cruise control, it's a change. You suddenly perform a change. Suddenly you see the whole performance comes over the step response, as you will see in this course very shortly. So it's significant for us. A step function. 1, put t greater than 0, 0 up to this. Okay. Look at this. My claim is the delta function can be viewed as a derivative of a step function. Okay? Let's look at, after all, you have looked at all this through the limiting what I do is this. This is your step function. At time t naught, I'm gonna go here. Instead of going vertically, I would choose ramp up with an extremely sharp, okay, with an angle 1/delta, okay? Vertically going up, your angle is infinity. I'm gonna go 1/delta, delta is 1 now. Is that clear? It's an approximation of a delta step function. You go like this. Limit. Step is a limit of this as delta goes to 0. Yes? Take a derivative of this guy. Derivative up to this point is 0. Right? Derivative from here is 0. Correct? What's the derivative here? 1/delta. So in that, derivative is this 1/delta. What is this guy? This is delta, 1/delta. That's the definition of a delta function. For any delta, yeah, I can take a derivative of a step. So you can say, yes, derivative of a step is a delta function. Are we good? Okay. Now, with this, I can do the Laplace transform. Okay?
Bro, this is technically DSP.
I think
Do some of it.
it's, remember, I had
I'm not even
this
paying attention.
already.
It's
Okay,
going
I
over
had
like
this.
time invariance,
Laplace
memory
transform,
lists,
the delta is
stuff like that.
I want you guys
Like
to.
I should be paying attention, but I
You
can't
have-
remember most of this shit
remember that
anyways,
page?
and I can't even read what he's doing.
Oh, yes. How many of you
These
remember?
actually don't seem bad, but they're all from the book. More like,
You remember?
Right.
I
you'll
showed
be
you.
fine. I'll send a link to my YouTube channel in case you want to get
What
caught up.
what book is this again? Because I bought a text, but I can't
This is
remember
what's
which one it
gonna
is though.
I
It's
saw
the
that
Controls
you
and
this
Systems,
So yeah.
8th edition. You got it on Parsons, I think.
Yeah, I think I do.
Yeah. I'll send you my stuff though.
So the Laplace of
because
this is what-
I found it online as a free PDF though, so I'm
suppose
not
I
sure
have
if the
delta
problems are the same.
and impulse response.
So,
Take a Laplace of both.
let me know if it is.
Yeah.
So Laplace of HT is equal what? H of S. Laplace of this is a linear time invariant impulse. Laplace of the output is equal to transfer function and Laplace of the input, correct? But Laplace of the input is 1. So Laplace of impulse response is equal to H of S. That's what you have to do. That's the connection between impulse response and transfer function. When you have impulse response in LTI device, you can go get a transfer function, take a Laplace. Or if you have a transfer function, get the Laplace inverse, go to the impulse. That's the condition. Okay. So do we use the impulse response in this course or no? Do I use like transfer function? We want to learn seesaw technology as it is practiced out there carefully and competence. But it is so important to know impulse response and more significantly state space model. I am going to come back at some point and teach you how to get the solution of state space model as well. Okay? But let's look at the concept of stability. Remember, there are two things drive our system. This is a data, which is a state of the system you learn at time t0, and you. This is what it is. Always when you think about the system, this is what it is. So when you think about stability, first of all, you have to understand what the stability means. Who came up with this word, something is stable? Like, we use it in a common language all the time. Oh, this thing looks stable, but it stays where you know, think about what comes to your head when somebody says something is stable. Okay? We have to start with stability for engineering is we deal with devices. They get excited because there's input. They have a response to the excitation, whatever they're excited. What you want, I write it here. This is the key, the language. The small causes the small. If excitation is a small, don't give me giant response to it. Okay? Think about it like this. Suppose the mechanical one. It does this. Bang on it. Somebody created. You don't want this car to go shaking like this. You understand this? You won't go shaking like this and just get by. That's called stability. Okay? That's called stability. Everything that we do, it has to be stable. But then we have to be extremely careful. What does that mean? Like here I have this guy and I have this guy. I can excite this thing by our data, secret, energy is stored in capacitor inductor, and see what the response to those energy is, which is internal. Or I can drive your circuit by external signal, which is external. So let's first create a language for ourselves. This is external, this is internal, okay? So when we think about stability, here we have external stability. This guy is internal. Why do we call it internal? Because it's energy that was inside your devices. This guy is internal. So we have two of them. Okay? External stability and internal stability. For obvious reason we call it internal. Because the data, etc., it means energy that was in your circuit. I didn't excite an external. It's a response to what you had internal. Does it dissipate or blows up? Breaks your circuits, okay? Okay, so let's look at one by one. The first one that we look at is external stability. Suppose there is nothing in your system. Suppose your system is relaxed. You excite some input. What we wanted to find the concept of stability. Okay. The concept of stability, external stability. Don't put the data equals 0, so my system becomes like this, you and me. It's a relaxed system. I'm assuming it's relaxed. I'm just focusing on external. Some signal goes in there, and some signal you see out there. We want small causes a small. What did they teach you guys? Bonded input produce bonded output, right? VIVO. You have to be extremely careful when you say VIVO. Extremely careful. For a system. Bonded input, you say, if I excited with a small magnitude. Suppose it's a teeny tiny signal, some noise goes to the system. It's really small. But suppose I have a bonded response, huge, that's bonded. That doesn't look like a small cause it's small, correct? That's not. In fact, as soon as your nonlinearity in your system is excited, that's absolutely not correct. It turned out the following. That engineers, when they hear this, they always have, it's really VIVO. They used to write it like this, with finite gain, WFG. In fact, some of the old engineering book, when you check it out, they used to do. The head is this. They don't stop at bonded input get bonded. No, there is another thing in their head. They said your device has a gain, fixed gain. Okay? Like a peak of output is equal to some numbers, say gamma, which is a gain of the times peak of input. that they know this. It turned out as soon as nonlinearity get excited, you don't have this. You don't have a finite. So let me just, so what in LTI things, in a very LTI device, CISO LTI device. So are you guys familiar with the norm or not? No understanding of norm. How do you define this, like RMS? Do you know what is? Everybody knows RMS?
Oh.
What's the definition of RMS?
Root mean squared.
What's it?
Root mean squared.
No, that's a name.
Yeah, it's like an average,
Average of what?
some signal, silence.
The square value of the signal. The average.
Yeah,
of the
and the
signal.
square value of sig. We have to learn this one a little bit more carefully. Yeah, I know they say square.
Power?
Somebody, what did you say, power?
Power?
Let's, no, let's, maybe, look, when you say signal, they should have taught you this. The engineers, they look at the signal.
They did, we don't remember.
For them, signal has a category. Okay? I'm gonna cover this thing for you because I do it. It's an energy signal. Or it's a power signal. So what is the energy signal? Energy signal, like if I give you f of t, what is the energy of it? You have to just write it down. If we assume that f of t is a current, go through the 1 ohm resistor, the energy that dissipate, okay? Learn what the energy of a signal is. Energy that dissipate. Remember that is Ri2, okay? R is 1, so it will be integral of the square of this guy over time from minus infinity, 0 to infinity, okay? That's energy signal. Energy signal, it turned out to be, immediately you can see that it has to be transient. They have to die up, so it's a transient signal. Otherwise they have infinite energy. So when the signal has infinite energy, what engineers they refer to it is a power signal. The power that dissipates, okay? Which you have to divide by the time, whatever energy divided by time. I'm gonna cover this, and so it's an energy power signal. And there used to be something they used to call monster signal, like a lamp, for example. It's the power of it actually is infinity. So they go, and then for each of them, they have a concept of size. And we will cover this thing. Mathematician, they call it L2, engineer, they call it energy, etc. We call it. But at this time, let's look at, I'm gonna cover one other thing. If I give you U of t, a signal, okay? I'm gonna define the size of this engineer, they refer to it as a peak. Peak of this signal. Peak means supremum of U of t. What is the maximum peak of overall t? Okay, peak. Make sense? It's a common sense statement that they use. Engineers, they are beautiful in the sense that they use the best things that it tells you. You know, it tells you what it is. If you go to the math book, they call this thing L infinity. You talk to engineers, they call it peak. Both of them are the same thing. Okay? So, peak. It is a concept of a norm and a size that engineers use. So in a BIBO, stability means, really if you look at the peak of an output, bounded, another peak, some numbers, 5 for example, or 4 or something. What engineers know is the following. This is what engineers see when they say, there is a gain here. Gain of the device, like an amplifier or something. I explain to you what is this gain. So gain, suppose it's 1.5 or 0.4, or any signal is fixed. So if you get the bounded here, if you put here with the magnitude epsilon, what do you get here? epsilon times 0.5, same order, mathematicians. So it's a small cause, it's small. So engineers, they know this. They know it's a gain trigger device. Okay? This disappears as soon as your nonlinearity gets excited. Okay? So always think about when you say EIBO, it is used, and therefore they don't talk to you in the textbook, etc. Because it's simpler to explain to you by this textbook. It's not something like a small causes bounded thing. It's not that, because there's a finite gain in there. Make sense? Always figure these things out. You're dealing with a device that has a fixed gain. And they used to write it actually, as I said, BIVO, and they use parentheses, WFG with a finite gain. They dropped this. But when you work, the gain is the critical one. What is the gain of this device? I'll explain to you how to compute the gain, okay? Let's see what time do we, I think we don't know. So what we want to start with the bounded input, bounded output stability. I'm not gonna write a finite gain here, but I'm gonna explain to you, it's just following whatever your book has written. I want all of you to remember that there is a finite gain. Okay? At this time, the question for you should be, if I have H of S, what's the gain of this guy that we are using in this stability context? Okay. So we have this linear device, say transform function G of S, Y of S equal G of S times U of S. U of S is the Laplace of input, Y of S is the Laplace of output. Impulse response is G to the lowercase g t, Laplace inverse of transform G. If you look at the impulse response, Y of t would be convolution, as you learned today. If I go to the impulse response, the response of this device is convolution of an impulse and input. Okay? Okay. I just wrote some stuff in a bounded input, you know. When I say something is bounded, you know, some example of it, etc. Signal that is not bounded. It's just about these things. Okay. I'm going to make it more precise as we go forward. I'm going to produce the concept of a norm. I have to define what is normal for you. Okay. How engineers, they look at the size of, and you learn what is RMS, okay, properly. Not just remembering the square root of 2, the blah, blah, blah. Suppose I have 5 sinusoids added, what is square root of what? Okay? Properly. And why they call it RMS, etc., etc. Okay? Just at this time one. We will cover all the norms, etc., etc. Okay. So we go with this definition. Bounded input produce bounded output. As I have pointed out to you, there is a gain involved. So you immediately pay attention that this satisfies the small causes is small. Okay? Do not forget the gain. That's the most critical things. Engineer always, when they see device, external stability, the next question is, what's this gain? That's the next question. Okay? Okay. The device is EIPO stable if your impulse response is absolute value. It converges. That's the result. From here, we will work it out, but I have to show this. If the impulse response of the device, if you integrate that from 0 to infinity, you get the final absolute value of it. Okay? That's, and we produce a bunch of tests for us that we will cover it hopefully next time. But I am good. You remember what it is. when we go from bounded input, bounded output, I'm gonna move you toward peak norm. Okay? We discussed the concept of various norm that engineers they use, etc., what it is. And we go from there. But at this time, we just simply go bounded input, bounded output, with the understanding that there exists a gain. And I'm gonna cover the gain next. Okay? Now we have to show this next time. Okay? Why such a thing is true? This is an if and only if result. Okay? If and only if result. Next slide. So homework the last time, this time you yeah. Did he respond to you? So maybe if homework is due Tuesday, right? But homework number 2, we always do it on Monday and pick up on Monday.
Okay, well, at least we know when he releases the homeworks every Monday.
Oh, okay.
Even though the previous homework's gonna be doing the following day,
Yeah.
Tuesday.
Yeah.